Okay, everybody. If you're watching this, it's because I'm not there. I know this is a surprise, but anyway, what I have here pictured is the contraption that you would be seeing today if I were there. So this is a hot plate. It's just a little burner here on top. It's got a little dial. You can turn up the temperature. And in it is a magnet stirrer. There's a little white magnet bar that you put inside the beaker, and then you can turn the motor up and it will spin that little magnet spinner, which mixes up the water, because this is water and ice is what I've kind of sketched here. So the water and the ice here would get mixed up by the little magnetic mixer that you can control from the hot plate here. So it's a hot plate, but then it's also a mixer, a stirrer, a stirring hot plate. How about that? So that's what we have here: hot plate, beaker of ice and water. This is a temperature probe. Of course, I have a ring stand. Wonderful sketch of a ring stand, and then I have the cable, because it's an electronic thermometer, and so the temperature probe sends off the signal to my computer. So that's the setup here. So we're going to take a look at what happens to the temperature as the water and the ice start to melt, and then the water is going to heat up, obviously, and then eventually the water is going to boil. And so the question is, what's happening during all of that? Well, before we actually get to that, I want to, because I can't remember who I told this to and who I didn't tell this to, but we need to look at particle diagrams for particles that can move. I don't think we've actually, I think there's only one class period. I can't remember who I did that. Oh my gosh. So we need to talk about what particle diagrams look like for these particles that can move now. So here's what I'm going to do. I'm going to draw, so this is for a solid. Oh, come on. Solid. Okay, then we have, I'll say liquid here. And then gas. I should have already sketched these on here. Okay. Gas. So if we think in terms of ice, being obviously solid water, and then liquid, of course, water, and then gas or vapor of the water. So the thing we need to do, and again, I did say this in, I think, only one of the classes. I was talking about this, but the rest of you, I don't think you've heard or seen this. What I asked for, since we have solids and liquids and gases all made of particles, and we've just been using like little, circles as the particles. The question is, how in a diagram can I make those look like they're moving? And if you think about it like this, maybe, if I have a car, like a cartoon, car, how would I show that car is moving in my sketch? So a car sitting on the road, how could I show that this car is moving? Well, I'm assuming that maybe you've seen a cartoon or comic or something like this, and there might be something like this. There might be lines of motion off the back of the car like that help us know, oh, they're trying to show that the vehicle's moving, and so they put some lines of motion on there. That could very well be it. So we call those, now, okay, I don't call them this. Someone I know called them this, and so I just kind of go with it when it's really kind of ridiculous. But they call them whooshies, which is just a ridiculous name. Whooshies. So I will probably refer to them as whooshies just because they did. And again, they're just lines of motion. So what does that mean? How does that translate into what we're talking about for particle diagrams? Okay, here we go. Particle diagram for a solid. The particles would be, oops, pretty close together, right? And in some kind of a regular pattern here. If I can, oh my gosh, some of them look square. Are you kidding me? Some of them look square. What? Okay, okay, erase that. Now, okay, this can be pretty bad. But how do the particles move in a solid? I'd say they don't have a whole lot of movement, so maybe we'll just say, oh gosh, 1 or 2 lines of motion. Oh boy. That's terrible. Oh boy. No, this is bad. That's bad. Okay, so there's a solid. They can't move a whole lot. They're not moving very fast. They're in a definite pattern, a structure. Now, let's just say that these particles now melt and become liquid. Okay, now maybe they're not in this specific pattern. They're kind of random now. They're not necessarily any further apart or closer together. But oh shoot, how many did I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There. So no longer are they in a pattern. And let's just say for instance that the liquid is actually hotter. It could be the same temperature as the solid, but let's just say the liquid is hotter, which means how would I indicate that it's hotter? Well, that means that the particles are moving faster, which means I would need more what? Whooshies. So maybe there's 2 or 3 on here. Now, if you're the class that I actually did this in, then I guess you can just fast forward this part. But if I didn't do this in your class, then you should be drawing this. And notice they're kind of random directions here. So the liquid particles, they definitely have more, they're more jumbled up. They're moving a little faster, I guess, than the solid. So I guess we've been heating up the liquid. And that's what it might look like. Now the gas particles, at that point, they've gained all of their freedom, all the freedom. So they aren't close to each other at all like these were. These were close to each other. The particles in the gas, they're not close to each other. They've completely broken away. So we have 1 here maybe, 1 here, 1 here, 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 5, 6, 7, 8, 9, 10. Okay, so how do I draw my whooshies on these? Well, the gas, I mean, if it's water vapor that just got boiled, I suppose it's pretty hot, but it doesn't have to be hot. Water vapor doesn't have to be hot, so it doesn't have to have a ton of whooshies. Maybe it's the same number of whooshies as it was when it was a liquid. So maybe there's just 2 or 3 on each of these. But again, the main difference is these have total freedom. They can go wherever they want. They're not connected to any of the other particles. So again, the goal is to show lines of motion as though these things are zooming around, flying around through the container. Hopefully that makes sense. So again, the point here, this particles in a solid, our diagram is describing how we described solids in class, where they don't have much space, they're in a rigid structure, they can't move a whole lot. Liquids, they're jumbled up a little bit. They can slip and slide past each other. They have some freedom. They may be going a little faster if the liquid's been heated up. Gas particles, complete freedom, no longer connected together at all, and they can go anywhere they want, all over the place. So there you go. That's what a particle diagram might look like for solids and liquids and gases. Now, back to my situation here, because I got to switch slides to go to a different graph here, because what I want to look at is what is the graph going to look like for ice water that's melting. All right, here we go to the previous slide. Oh gosh, it's already at 10 minutes. This is ridiculous. Okay, so here we are on this slide. This is the graph that if you were here today, you're here. I'm not there. So if I were there, this is what you would see. You would see a graph start to form. There'd be a little red line down here at the bottom at 0 degrees Celsius. Because really, and you may not believe this, and it would probably look a lot like this, where it'd be kind of going up and down and kind of zigzagging. What's happening during this section of the graph? Well, I'll tell you what's happening during this section of the graph. The heat is on, the ice is with the water. Notice what the temperature is reading. The temperature is reading 0 degrees Celsius, which is the freezing point of water, or of ice, which is water. So, that also means that ice melts at 0 degrees. So if ice melts, if that's the melting point and the freezing point, then both things happen at the same temperature, which means water, H2O, can exist as a liquid or as a solid at 0 degrees. So 0 degrees, water can be either a liquid or a solid. And so what we would be seeing is that we have ice water that's hanging around here at 0 degrees, and the temperature's not changing, even though the amount of energy is increasing. So it's been heated the whole time, and yet the temperature is not going up. And then finally, what we would notice, as there's just these tiniest little bits of ice left, we would see this line, we'd see the line start to curve upward. And then it would kind of go at a pretty steady rate like this. And again, what's happening during this section? Well, the water is heating up. And look what it's approaching. The water is approaching what temperature? The boiling point. And you would see the line start to level off like this and do that right there. Now, what is this actually telling us? Well, follow along with me. During this section, ice is melting. Okay? During this section, the water is actually heating. The water is getting hotter. Once it reaches the boiling point, what happens? The temperature stops going up, because water cannot be a liquid and be above the boiling point. It stops. The temperature stops going up. Now, you're going to need to write. I hope you've been writing all this stuff down. Lord have mercy. You better be writing this stuff down. Now, here's what I'm going to tell you. Okay? During this section, we had melting. Yeah? Oh gosh. This stylus is terrible. Oh my gosh. Melting. Not metting, melting. And here we have, I should probably erase that, but I'm not gonna. Here we have liquid, oh my gosh, this thing's terrible. Liquid heating and here at the top we have boiling. Now, here's what I want to ask you. Where on this graph are phase changes happening? Where on this graph are phase changes happening? If you're saying here, then I agree. There's a phase change. That's melting. Is water heating a phase change? No. It's just liquid getting hotter. Is boiling a phase change? Well, yeah, it's evaporation. It's rapid evaporation. So boiling is a phase change. Melting is a phase change. Question: what isn't happening during a phase change? Look at the graph. What is not happening during a phase change? No temp change during a phase change. Write that down. There is no temperature change during a phase change. So while the ice is melting, the temperature cannot change. All of the energy that's being given is going to breaking down the structure of the ice. It's breaking down the structure. Once the structure is all gone, then the water can actually get hotter, which means the particles can get faster. Once the boiling starts, the water particles cannot get any faster because they're already at 100 degrees Celsius. They're not going to get any faster. But what are they getting? Are they continuing to absorb and gain energy? Yes. But what's happening? The temperature's not going up, but the particles are gaining what? What are they gaining? Total freedom. All right, let's try to write some of this down. Maybe it will make sense. I don't know. So, during the melting process, we have ice. Oh gosh, ice gaining. Oh my gosh, energy. I'm going to have to just abbreviate. You're going to have to write like clearly as I speak it. I mean, this writing thing's just not going to work. Okay, so ice is gaining energy. I should say particles. Particles. Ice particles are gaining energy. And the structure is breaking down. Structure. Oh my gosh, structure falling apart. So the structure is breaking down, falling apart. That's what the energy is getting us. Now here, during the heating phase, during the liquid heating phase, we have H2O particles that are what? H2O particles are doing what? They're getting, finish the phrase, they're getting what? I hope you're thinking faster. They're getting faster. How do we know they're getting faster? Because they're heating up. That's what it means. Heating up means they're getting faster. Are these particles getting faster? No, because their temperature isn't changing. The temperature's not changing, so they're not getting faster. Where's all the energy going? To breaking the structure apart. That's where the energy's going. The temperature can't change while the structure is falling apart. Once it's all liquid, now the particles can get faster. They're gaining energy, getting faster. Oh, you should probably write gaining energy here too. So they're gaining energy here. They're gaining energy here. So what's happening here? Are the particles still gaining energy? Yes. Particles, oh gosh, particles gain energy. I'm just going to say E. Particles gain energy during the boiling. Are they getting hotter? No. No temperature change. They're not getting hotter. They're not getting faster. What are they doing? Gaining what? Total what? Freedom. They are gaining total freedom. Okay? That's what they're getting from it. So, phase change, no gaining temperature. Phase change, no gaining temperature. Are they gaining energy? Yes. Particles gain energy here. Particles gain energy here. Particles gain energy here. Although I didn't write it, you should probably write that. Gain energy. Particles gain energy. So, I hope this makes at least some sense. I wish that I were there to show this to you, but this is exactly what would happen. It may not be exactly this pretty, but it's going to be very level here. It's going to slowly start curving up, increase temperature, then it's going to completely level off, just like you see here. So, I think that's all I need to tell you. Gosh, that was quite a ways. Now, with that information and everything else you know, you should be able to finish that worksheet. We will talk more about it on the block day, and hopefully you'll be ready then for the test at the end of the week. See ya later.